Okay, so here we go to talk about infinite series. So we've already talked about infinite sequences and whether or not an infinite sequence converges or diverges. It was all about the terms of the sequence and whether or not the terms of the sequence are approaching a single finite value. If those terms of the sequence are approaching a single finite value, then we say that the sequence converges. If not, the sequence diverged. So here let's look at a series. Now, a sequence and series are a little different. A sequence is a list of terms, and finite or infinite, depending on whether you're talking about a finite or infinite sequence. A series is a sum of terms. So let's look at this. So if we have a sequence a sub n, and that happens to be an infinite sequence, then if we look at the sum of a sub n, so we look at the sum of all the terms of the sequence, we would have an infinite series. Okay? So what's the difference between sequence and series? A sequence is just a list of terms, and we're talking about infinite sequence, an infinite list of terms. If we then took those terms of the sequence, which there's an infinite amount of them, and added them all together, that would be what we call an infinite series. So these terms themselves here are just the terms of the sequence. If we then add them together, we have an infinite series. Okay? A finite series is boring because a finite series is just a finite sum, and a finite sum will always be a finite value. There's not much to that. Even if it's a million terms that you're adding together, it's still going to end up being a finite value. It's just a matter of taking the time to add all those terms together. It's the infinite series that's far more interesting. Because the question comes, if I add an infinite amount of terms together, do I get an infinite value or a finite value? And sometimes one, sometimes the other. So we got to figure out what's happening here. So there's a bunch of ways to determine whether or not an infinite series adds up to a finite value or an infinite value. The way we start by doing it is by talking about something called partial sums. So let's just give you a first quick introduction to partial sums before I go into this definition of convergent and divergent series. So if I said we have a series, okay, an infinite series, say a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, etc. A partial sum is to only add up a part of that sum, hence the term partial sum. So the first partial sum, which we could label as s sub 1, would just be the first term. The second partial sum, which we'll label s sub 2, is the first two terms added together. The third partial sum, which is s sub 3, will be the first three terms added together. You see the pattern. So then if I said the nth partial sum, s sub n, it would be the first n terms added together. So a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, all the way up to eventually whatever a sub n is for some random n value. So those are what we call partial sums. We can figure out what these partial sums are, and they each would have some value to them. Okay? Because these are finite sums, we could do this addition and add them all up and figure out what the answer is. Now, the idea with this definition of convergent and divergent series we're going to look at in a second is to look at the answers we get for each one of these partial sums. Well, what that's going to create is a sequence. This is a term, this is a term, this is a term, this is a term, and this will be a list of terms. And so this is what we call the sequence of partial sums. All right, so now let's look at the definition. It says, for an infinite series, say the sum of a sub n, the nth partial sum can be found by adding the first n terms, which we'll label as s sub n, so a sub 1 plus a sub 2 all the way up to a sub n. If the sequence of partial sums converges to, say, s, then the series converges. Not only that, the series converges to s. The limit s is the sum of the series. Okay? And this says if the sequence of partial sums diverges, then the series diverges. So we just spent a whole class previously determining whether or not a sequence could converge or diverge. And we're going to use that to help us figure out if a series will converge or diverge. Because if this sequence of partial sums, which is these sums that we are getting as we add more and more and more terms, if we can figure out if this sequence here converges, then the series will converge. If this sequence diverges, then the series will diverge. So we're using what we know about sequences to help us determine the sum of an infinite series. And not only that, the other good thing about this is whatever this sequence converges to, that's what the series will converge to. Now this should make a lot of sense just using, your basic common sense here. What are we doing when we're finding a partial sum? We're adding more and more and more and more terms of the corresponding series together. So as we keep adding and adding and adding and adding and adding, what happens? Well, we're getting closer and closer and closer to what the actual sum could be. So if we're adding and adding and adding and seeing that after we add one term or two terms or three terms or 2,000 terms together, we're getting answers that are getting closer and closer and closer to some finite value, then as we keep adding and keep adding forever, we should probably continue to keep getting closer and closer to that finite value. And therefore, the sum of the infinite set of terms should add up to that finite value. Let's do some examples, and hopefully it helps a little bit to understand what we're talking about here. Okay, here's our first example. So it's the sum as n equals 1 to infinity of 1 over 2 to the n. So sometimes it helps to look at the terms of this series. So when n equals 1, I plug 1 in for n, I get 1 over 2 to the first. That's the first term. Plus, now I'll plug in 2 for n. So 1 over 2 to the second would be 1/4. Then I'll plug in 3 for n. 1 over 2 to the 8, 1 over 2 to the third, which is 1 over 8. Then 1 over 16. Then 1 over 32, etc. And this will just keep going and going and going forever to infinity. This is an infinite series. So the question is, as I keep adding and adding and adding all these terms together, they're all positive. If I add them all up, do I end up getting a finite value for that sum or an infinite value for that sum? Does the series converge or diverge? And if it does converge, can we figure out what it converges to? What does the sum add up to? So it says in that previous theorem, let's look at the partial sums. So let's look at the first partial sum, which is 1/2, just the first term. Then we'll look at the second partial sum, which is 1/2 plus 1/4, which is, in our case, 3/4. Okay? Then we'll look at the third partial sum, which is 1/2 plus 1/4 plus 1/8, which will then be 7/8. Then we'll look at the fourth partial sum, 1/2 plus 1/4 plus 1/8 plus 1/16. If you added all that up, you would get 15/16. Okay? So then if we looked at this and said, all right, well, what does the nth partial sum look like? If we add up the first n terms, so 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus blah, 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 1 over 2 to the n. Is there a pattern to these numbers that you're seeing here such that if I wanted to find, say, like the 1,000th partial sum, if I plug 1,000 in for n, would I just get the answer? The idea is you definitely see there's a pattern to this. So the pattern that you're seeing is in the bottom, you have 2 to the n, and at the top, it's always 1 less than that. So 2 to the n minus 1. So this is the formula that would generate this sequence. When I plug in 1, I get this. When I plug in 2, I get this. When I plug in 3, I get this. Plug in 4, I get this. Plug in 1,000, I could figure out what the 1,000th partial sum equals. Okay? So that tells me if I was to add the first 1,000 terms of the series, I could figure out what my answer is. All right. Now the question here, does this sequence of partial sums converge or diverge? What is the limit as n goes to infinity of the sequence of partial sums? So this is where what we learned about sequences of partial sums converging and diverging will come into place. So what we said is if we could come up with a function that would generate the terms of the sequence, if we could take the limit of that function and find out what happens to it, which happens to be sitting right here, then that'll tell us what happens to the sequence. So if I do the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n, which using L'Hopital's rule, we're going to find out equals 1. Mainly because when you go to do L'Hopital's rule, this is an infinity over infinity limit. The derivative of this will be the same as the derivative of this. So then they'll cancel each other out. Now I take the limit of 1 and I would get 1. So anyway, since the sequence of partial sums converges to 1, since the sequence of partial sums converges to 1, then the series 1 over 2 to the n also converges to 1. So we got two things out of this. The infinite series converges, and it converges to 1. So if I add up all these terms, the total sum should equal 1. All right, there's an alternative proof for this that has nothing to do with necessarily this sequence of partial sums. Well, it has a little bit to do with the sequence of partial sums, but it's more geometric in nature, just to further hit home the fact that this equals 1. Now, it only really works for this example. We can't keep using this over and over again, but it's a pretty simple one, so it's not bad to see it. So if I give you a square, that's a 1 by 1 square. The area of that square is 1. So no matter how I divvy the area of this square up, when I put it back together, the whole area should equal 1. So let's cut it in half. This is now a half, and the other side would be a half. So I'm going to cut that in half, though, and this piece would be a quarter. Then I'm going to cut the remaining piece in half, and this piece would be an eighth. You kind of see a pattern developing similar to the terms of the series. Then this would be a 16th, and I keep cutting in half and keep cutting in half and keep cutting in half and keep cutting in half. And I can keep doing this technically forever. I mean, me physically, I can't do this right here on my laptop because eventually I can't zoom in any further, and my thickness of my line will just fill in the space. But if I could zoom into this infinitely many times, and I could keep cutting in half and cutting in half and cutting in half, I mean, whatever you have something, you should always be able to cut it in half. Then the idea is when I put all these pieces back together, which is essentially adding all these terms back together, I should get back to whatever the total area is, which is 1. So this further shows that if I add a half plus a quarter plus an eighth plus a 16th plus a 32nd, etc., and keep going and going forever, my sum should equal 1. Again, that doesn't really do a whole lot for you as we move forward. The partial sum concept, which we see here, is what's going to get you your answers. But this just further hits home that if you add an infinite amount of things together, you could get a finite value out of it, even if all those things you're adding together are positive values, which is a little abstract. And if you think about, if I keep adding and adding and adding and adding and adding positive values together, you would think it would keep getting bigger and bigger and bigger. But we've seen this before, that when we looked at the improper integrals, and we talked about the areas that went on forever, and the areas that went on forever actually were a finite value. It's the same concept, right? Here's another example. So if I look at this series, which is a pretty simple series, the first term of the series is 1. If you notice, there's no n's here. So when n equals 1, this term is 1. When n equals 2, the term is 1. When n equals 3, the term is 1, etc. So what this series is just 1 plus 1 plus 1 added over and over and over and over again. So if I add 1 plus 1 plus 1 plus 1 and do that forever, I think right away everyone could probably get a guess that this is probably going to diverge, that this is just going to keep getting bigger and bigger and bigger and bigger and bigger and not get close to some finite value, but actually go to infinity. But that would just be a guess. We need to kind of show that a little bit better, so let's do it with partial sums. What's the first partial sum? Well, it's 1. What's the second partial sum? Well, it's 1 plus 1, so 2. What's the third partial sum? 1 plus 1 plus 1, 3. What's the fourth partial sum? 1 plus 1 plus 1 plus 1, 4. So if I said, all right, well, what about the nth partial sum? If I had the first n terms, 1 plus 1 plus 1, all right, well, I'm going to do that n times, right? So the sum would be n. So now look at this sequence here. This is the sequence of partial sums. This is the formula for how I generate that sequence. So if I took the limit as n goes to infinity of that sequence of partial sums, which is really just a limit as n goes to infinity of the formula for the sequence, which is really just n, I get infinity. So this sequence here, 1, 2, 3, 4, 5, 6, 7, all the way up to whatever n is, right? That sequence clearly diverges because it's going to get bigger and bigger and bigger and bigger and bigger. So the sequence of partial sums diverges. Therefore, the series also diverges. When something diverges, you never say what it diverges to. The series just diverges. So again, using this sequence of partial sums to help us figure out what happens with the series is one way to do this. Now, I'm going to give you some information that's going to come up real quick, and that is this concept is fairly easy to understand, but very hard to put into practice. I'm giving you easy examples right now because those are the only ones for which this works. But this really starts falling apart fairly quickly as we look at more and more and more examples. So we're not going to be doing this forever. We're going to have a lot of other ways to determine if a sequence converges or diverges. But for right now, this is the best way to start the concept of, does an infinite series converge or diverge? All right, so here's another one. This one is a little more complicated than the previous two, but we can still use the partial sum concept. If you look at this series, there's something very unique to this series that we're going to talk about. Let's look at the first couple terms. So if I plug 1 in for n, there's 2 pieces to every term. This whole thing right here is one term. So I plug 1 in here and 1 in here. So I get 1 over 1, which is 1, minus 1 over 1 plus 1, which would be 1/2. That's the first term. Plus, then I'm going to plug 2 in for n here and here. So I get 1 over 2 minus 1 over 3. Then I'm going to get 1 over 3 minus 1 over 4. Then I'm going to get 1 over 4 minus 1 over 5, etc. And that's going to continue on forever. And I think you start to see something happening here. So let's look at the sequence of partial sums. The first partial sum is 1 minus 1/2. I'm going to leave it like that. The second partial sum is 1 minus 1/2 plus 1/2 minus 1/3. And what you see is these halves cancel, so we end up with 1 minus 1/3. Third partial sum, 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. And you see all this stuff inside cancel out, and we're just left with 1 minus 1/4. Let me go one more. Fourth partial sum, 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5. And all this cancels except for 1 minus 1/5. I'm not going to actually do the computation of 1 minus 1/5 or 1 minus 1/4. It's not necessary. So what we see here is this right here is the sequence of partial sums. All these inner terms are ended up canceling out. What we call this type of series is a telescoping series. When all the inner terms of the sequence start canceling, we refer to this as a telescoping series. So all you're really left with is the first term and the last term. So the sequence of partial sums for this one would end up being 1 minus 1 over n plus 1. That's the formula for how I would generate this or this or this or this when n equals 1, then n equals 2, then n equals 3, then n equals 4. If I want to find, say, like the 1,000th partial sum, it would be 1 minus 1 over 1,001. That would be the answer for adding the first 1,000 terms together, because all the inner ones would cancel. So let's look at the limit as n goes to infinity of the sequence of partial sums. And since we're able to figure out a pattern to this sequence, and therefore the formula to that pattern, which is really the key to being able to come up with the whether or not the sequence converges or diverges, and that's what we saw. There are other ways to determine if a sequence converges or diverges, but the primary way, and at least the easiest way to determine if a sequence converges or diverges, is to have a formula for that sequence that we could take the limit of. So if we're doing that, which we do have, we do the limit as n goes to infinity of 1 minus 1 over n plus 1. And if you did that limit, the limit of 1 is just 1. 1 over n plus 1 as n goes to infinity, that goes to 0. So we just get 1. So this sequence of partial sums converges to 1. The sequence of partial sums converges to 1. Therefore, the series converges to 1. So we figured out that the series is going to converge and what it converges to. So that's two questions that we're answering with every single one of these infinite series. Does the series converge? And if so, what does it converge to? Now, sometimes we'll be able to get both of those answers, and this sequence of partial sums concept gets us both of those. As we move through the next couple of lessons, we might not be able to answer both of those questions immediately. We might be able to figure out that a series is going to converge, that the series is going to be equal to some finite value, but maybe not know exactly what that finite value is. So anyway, we call this a telescoping series, like I said. A telescoping series is when we have the inner terms of the series all collapse on themselves, is why we call it telescoping. It's how a telescope works. Only sort of like an old school, like pirate telescope, collapse on itself. So anyway, we're left with the first term and the last term. And the idea is the first term is always going to be some finite value. I mean, it's going to be some number, because you would have plugged, say, 1 in for whatever n is, and you would have got something out of it that's finite. It's all about the last term that you're left over with. If that last term, okay, that you're left over with, this piece right here, if the limit of that ends up approaching a finite value, if this approaches a finite value, not necessarily 0, just a finite value, then you have some finite number here minus some other finite number here for your limit, and your limit as a whole will be equal to a finite value, and therefore the sequence will converge. But if that last term here does not approach a finite value, then that's going to do the exact opposite thing. So the series will converge based off of the limit of that last term. So let's just give you a hypothetical. Let's say, hypothetically, we had a sequence of partial sums for a telescoping series where the first term was 5 minus the pattern for the last terms was n squared over n plus 1. So if I want to find the first term, I plug in 1 for n, and that total thing right here would give me the first term. If I want to figure out what the 1,000th term is, I plug 1,000 in for n, and that would give me the first 1,000 terms all added together. But look at this thing right here. If I look at this as n is getting bigger and bigger and bigger and bigger and bigger, what happens to that? As n goes to infinity, that thing goes to infinity because the numerator is bigger. So if this piece goes to infinity, then the sequence of partial sums is going to go to infinity, and therefore the sequence of partial sums will diverge, and then the series will diverge. So this has everything to do with the telescoping series converging or diverging. Not every telescoping series will converge. Some will, some won't. It's all based off of that last term. All right, here's a good example that I like to give right about now because it seems like a really simple series. There's not a lot going on with it. It seems fairly simple to work with, but it's not actually that easy to use this partial sums concept with. So it shows you the downfall of this partial sum idea. So this series, if you looked at it, you know, the first term was just 1, the second term is a half, third term is a third, then a fourth, then a fifth, added over and over and over again. Now I'm just plugging 1 in for n, then 2, then 3, then 4. It's a pretty basic series, not a whole lot going on there. The problem is the partial sums. The first partial sum is 1. No big deal. The second partial sum is 1 plus a half, which, if we added that up, 3 halves. The third partial sum, 1 plus a half plus a third. So if we added that up, what, 3 halves plus a third is 6. So what's that? 9, 11 sixths. Does that sound right? Okay, if we look at, say, like the fourth partial sum, 1 plus a half plus a third plus a fourth. So what are we going to get? It would be 11/6 plus another fourth, so it would be 24 as a common denominator. So let's go, what, 44 plus 6. So what's that, 50 over 24? Yeah, I could simplify that, but let's just keep leaving it like that. I'll go one more. Fifth partial sum, 1 plus a half plus a third plus a fourth plus a fifth. So what's the common denominator? Be 120. So what? 250 plus 24, so 274 over 120. All right. So if I just said, here's a sequence. And if you wanted to simplify these fractions, you could, but it's actually usually easier to find a pattern without simplifying. Could you tell me what the formula for that sequence is that would generate that sequence if I plugged in 1, if I plugged in 2, if I plugged in 3, if I plugged in 4, etc. So what's the sequence of partial sums for the nth partial sum? Well, the bottom's pretty easy. It's n factorial. Okay? Question is, what about the numerator? So we got to plug in 1 and get 1. Okay, that's not a big deal. But plug in 2 and get 3. Plug in 3 and get 11. Plug in 4 and get 50. Plug in 5 and get 274. That is going to be a little bit harder. And so we could sit here and try and work on it, and maybe eventually we'll come up with an answer for the pattern of partial sums. But it's going to be fairly difficult, is the basic idea I'm trying to get at here. So if we can't come up with a formula for the sequence of partial sums, then if we want to look at whether or not the sequence of partial sums converges or diverges, if we want to take the limit of the sequence of partial sums, that's going to be extremely difficult to do because we can't do what we've been doing. We don't have a function that we can take the limit of. Now, there are other ways to find out whether or not a sequence converges or diverges, but when we were talking about that in the previous lesson, we saw that those were not the nicest thing to do. So this problem is far more difficult than the previous problems, mainly because of this. Coming up with a formula for the sequence of partial sums is extremely difficult. So the question is, does this sequence converge or diverge? Well, we don't know. Okay, this partial sum concept kind of has met a roadblock. So for right now, to be continued. It would help if I could spell it. To be continued. Okay? We'll figure out a way to do this, but this partial sums way, probably not the best way to do it, which then tells us we need to come up with other ways of determining whether or not a sequence is going to converge or diverge. Now I'll give you just a sort of a foreshadow to where this is going to go. This one's going to end up diverging. Okay? But we need to figure out why.